So it's to avoid ambiguity. The molecular formula showed you how many of a type of atom, and to name this, we'd call it sodium chloride. The main reason why naming conventions are important for chemistry is because it allows chemists around the world to communicate with one another. So if you imagine scientists that speak the English language have naming conventions of their own, and French scientists may have naming conventions of their own, and Chinese scientists may have naming conventions, then communicating scientific breakthroughs between those different languages becomes difficult. So the reason why we keep naming conventions international is because we want to allow chemists to communicate with one another so that in terms of research, the field of chemistry can grow much faster. People aren't repeating the same experiments because things have different names. So that's the main reason. Similar to what maths is considered quite a universal subject, and many people enjoy the idea that maths can be used to communicate with anyone who understands maths as well. Similarly here, chemistry can be used the same way. Chemical names are all the same across the world. It allows chemists to talk to one another about chemicals and new chemicals that are developed. Because of the huge amount of chemicals in the universe, just the huge vast majority of them, a naming convention also helps to avoid ambiguity or confusion. Other than this one, the other one here is that there are a lot of chemicals that look very, very similar but have very, very different properties. If we don't name these correctly, we could have a situation where chemicals that aren't supposed to be mixed together may be mixed together because we didn't understand the different naming conventions. So it's to avoid ambiguity between chemicals that look sort of similar. These two are the main reasons. So in order to talk about naming chemicals, we need to know what a chemical formula is. So the first one is the molecular formula. Now this shows the actual number of each kind of atom in a particular molecule. For instance, we're going to talk about this one, C2H6, which is called ethane. Now a molecular formula like this shows you that there are 2 carbon atoms and 6 hydrogen atoms. And so that is the molecular formula for this chemical. However many atoms you have of that particular element, just put them all together and put the number, and then that's what the molecular formula is. Now the empirical formula is slightly different and slightly more confusing in that it shows the number ratio of atoms. So what it does is it takes the smallest ratio of atoms, and that is your empirical formula. And that's often used in very long polymers like cellulose and things because it'd just be impossible to write out every single number. So we just simplify it for analysis purposes. Ethane again, we had C2H6, right? So for every 2 carbons, there's 6 hydrogen. So we can actually reduce that ratio to be 1 to 3. For every 1 carbon, there's 3 hydrogens. So then we can just write this as CH3, and that's what we've got here. So it's just the lowest ratio. And often you won't encounter too many of these empirical formula in your study of chemistry, but it's just here just to show you in case. So empirical formula, the lowest ratio, and it's quite confusing when you look at it. And lastly, this is my favorite one because it shows you the most about a particular chemical. It's the constitutional or structural formula. I use this one all the time. And it shows the arrangements of atoms in a molecule. So the molecular formula showed you how many of a type of atom were in a molecule. The empirical formula showed you the ratio of atoms in a molecule. And this one actually goes beyond the molecular formula and shows you what it looks like. So here we have the ethane molecule again. So you've got 2 carbons bonded together, and then you've got the 6 hydrogens all around. And that's what it would look like. Sometimes, if we don't want to draw all this, we can have a sort of abridged version. You could reduce it down to a shape like this, where you've got repeating elements sort of like this, just to reduce the complexity because we don't want to keep drawing this all the time. So you can actually reduce it, get it down to its most significant parts. Now that we've seen the different types of formula, we're going to try and name salts now. What are a salt? Well, a salt is simply a compound formed from a metal, so the left-hand side of the periodic table, and a non-metal, so the right-hand side of the periodic table, through an electron transfer reaction. You've transferred an electron from a metal to a non-metal, and you've got sort of a bond, and that is a salt. And now we're going to try and name salts. So when naming a salt, the metal's name comes first. Okay, so if I was mixing sodium with chlorine, we get NaCl, and to name this, we'd call it sodium chloride. So the non-metal, the reason why I said chloride was because the last 3 letters of its name, the non-metal that is replaced with the suffix "ide." The metal comes first, normal name, sodium. Now we've got chlorine. So we drop the last 3 letters, I-N-E, and then we add "ide," so it becomes chloride, so it becomes sodium chloride. For instance, magnesium and oxygen, here's another one. Got magnesium, and then you drop the N bit and it becomes oxide. So you take the first sort of syllable and add "ide." Now what about nonmetals? Because we see a lot of non-metal compounds all the time. So an example of this would be CO2. That's a non-metal compound. Neither of them are metals. So how do we name that? If you look at a periodic table, the substance that is furthest to the left is listed first. So in this case, CO2. Which one of these is furthest left on the periodic table? If you look it up, you'll see it's C, carbon. So we say the first part is carbon. The other part has the "-ide" suffix applied to it. Same thing. This part has the "-ide" suffix and a multiplier at the front depending on the number. The multiplier can be mono, meaning 1, di, 2, tri, tetra, going on. Two of them means di, so it's carbon, di, ox, ide. Carbon is the first thing that we write. Then we put the number of the other element, which is di. Then we put the first syllable of the other element, which is ox. And then we add ide. And now we have the final chemical that we're all familiar with, carbon dioxide. There are also things called composite ions. There are compounds that contain ions that are made of more than one atom. For example, the hydroxide ion, OH-, is an example of this. The sulfate ion, SO4 2-, ammonium ion, all of these are ions made of more than one atom. And to know these names, you need to know their valency. You need to know these numbers at the top. Otherwise, you'll stuff up the combinations. So let's look at NaOH. You take the positive ion's name, first the metal, which is same as before, metal, sodium. Then you add the negative ion, and then you get sodium hydroxide. In cases where you've just got the two different ions, then it's easy. Just positive ion first, then negative ion, and that's your answer. So the hydroxide ion is what we have. The sodium ion is what we have. And you just put them together, sodium hydroxide. Very easy. So that concludes today's lesson on naming compounds. So we've looked at naming salts, non-metal compounds, compounds containing composite ions. So we've looked at also why is it important to have naming conventions, and what are different types of formula we can use to represent these chemicals. Okay. So this is all very confusing and it's new, and I understand that it's new to you. So we'll go on to the question segment. Hopefully that'll clear up some of the questions that you might be having.